My name is Vincent Berk. I'm the CTO and Chief Security Architect at Riverbed. I'm going to tell you about what our visions for the future are. Now, we've talked about this at prior tech field days, together as well. So these topics should seem somewhat familiar to you. But one of the key things I do for Riverbed is I try to sleuth out what it is that people are buying our collection of visibility tooling for, right? Because it helps us think about what we need to build for the future. And one thing that is absolutely obvious is that everybody is trying to get the resolution of problems as quickly as possible, right? We call this root cause analysis, right? And I want to set this distinctly apart from the idea of just visibility alone, because visibility is a fairly broad word, right? So a lot of things are visibility, right? Like an endoscope is visibility, right? You can go and poke it in your knee and figure out what's happening on the inside of it, but I don't have a need for it, right? I'm not a surgeon. I don't need to be looking inside, and therefore I don't have a need for that kind of visibility. What we're really doing instead is we're providing visibility so that the operators can perform root cause analysis, right? Now, necessarily, there's a couple of things that are going to be happening and why this is visions of the future, right? So the network has started to invert a bit, which is what you've already brought up. We're seeing infrastructure as a service, we're seeing lots of containerization, we're seeing SaaS services, and we're also seeing work from anywhere, meaning that the path of the network has now become sometimes much harder to see, right? So I'm going to talk about that in a little bit, but I want you to sort of put that already in the back of your mind as it's gotten more complex, right? And this is like, people always say that, right? Networks have gotten more complex, but what do we really mean by it, right? So, well, in the old days, when we had an office, and in the office there was a data closet. The data closet had servers in it. We had one application per server running, and then everybody sat on the network wire, and you monitored that, and it was at least organized in our minds on how that was done. And then, we started moving things out to data centers. We created these crazy tunnels. Then we made software to direct those tunnels around. We got the SD-WAN out of it, and it all made some things easier, but it made it harder to troubleshoot root causes of productivity issues, right? So that has made for root cause analysis has gotten much more complicated. So when I take a look at what our customers do, is they're spending all their time trying to sleuth out one piece of data with another piece of data, trying to look at, okay, is that related? Is it not? To try to get to that conclusion. And this is why I think the absolute key of solving problems in this space is correlation, right? I call root cause analysis. There's the three C's of root cause analysis. They're correlation, correlation, correlation. There is nothing else but correlation. And so, what I've done here on the right-hand side, this is, some of you might have seen this in a networking field day presentation. It's actually a different slide, but I like my dog a lot, so I decided to put that dog back up there. The point what I'm trying to make with the doggies here is that, the top one is an X-ray, then there's an MRI, and then there's a visual of the dog, but it is three completely different angles or visibility points on the same observed environment, right? And by doing that, right, and you could say like that's packets, it's flows, it's synthetic tests, or what have you, all the things that Phil was talking about. But by taking those different and diverse sources of data, observing one environment, I'm able to start making correlations in my mind. And I'm starting to say things like what's on the left, right? VoIP calls drop when one particular interface has a retransmit rate of over 5%, or when the CPU in the router is busy, I see a lot of drop packets on this link, and I see a lot of fragmented flows happening, right? These things all go together. Not only that, it also always happens Tuesdays afternoons and Friday afternoons, right? And if I can get closer to solving that correlation problem for our operator will have a much quicker time to resolution in an ever increasingly complex place, right? So bear with me on this conversation. I put another example in there because we're pushing to the endpoints. And with endpoints, I mean both endpoints, right? Applications are slow, but they're only slow for Phil. Not only that, he has an unusually high memory usage for what he normally does. And I know Phil's got 34 tabs open per browser, but not just that, he's using a lot more this time. And there is a Monero miner running on his computer. Okay, interesting, right? So that could be absolutely right. And if I can get those pieces of data together, I can do that scope analysis for the operator, then they don't have to do that on the whiteboard. Now, when I talk about root cause analysis in the future, right, Riverbed keeps a certain depth to its data. But when you have depth of data, then finding a root cause of problems and finding the root cause of security incidents are really actually the same thing. Think about it. The network is slow, right? Phil talked about it. Well, is it slow because the router is broken or the software has a bug, or is it slow because somebody is exfiltrating 10 terabytes worth of email data out of my network, right? I actually really don't care. I want you to tell me either of those root causes. I want to just know the root cause, right? Like, we can't simply say there's performance and then there is security and Riverbed's a performance company. In fact, by being a good root cause analysis company, we have automatically also become a security company. And that's just two of the pillars. If I talk to customers, what I find that the pillars that Riverbed is increasingly needing to focus on, it's performance, cybersecurity, but also usage and cost analysis. Right now, Phil talked about cost analysis and tying it into business metrics, but we also see a lot of usage questions coming up, and questions of, geez, I moved my branch racks to a data center. You guys helped me figure out what would break and if there was enough bandwidth. And then, a few years ago, we had, okay, data centers and move it to infrastructure as a service. Can you guys help me figure out what would break when I do that, if there's enough bandwidth, where the bottlenecks are? And just yesterday, somebody said, hey, we're going to have all these people moving back into the office from work and from home. And they've now started getting used to higher bandwidth applications like the Zoom call we're on right now. And people are starting to wonder, okay, is there enough bandwidth in the office now to support people coming back into the office? So anytime there's a change or a migration, people fall back to Riverbed to try to figure that out, right? So here's really the point, right? Like, I'm not going to go over what it means to be a full fidelity company, but Phil hinted at it. Riverbed's an open-ended problem-solving company, right? The problem is open-ended. We're going to come back to that in just a second. So in the world of petabytes, we've talked about packets, right? I heard that loud and clear. Where do you store this stuff, right? Like, how do we handle these large volumes? And when I talk petabytes, I mean petabytes. There's some of our customers deploy multiple of these petabyte appliances that we have. I can't hopefully bring it all together for you in one central portal, or let's call it the data lake, but I'm not fond of that word, because it's gotten such a negative connotation. The point is, it's intractable of a problem. I need a strategy. I need a strategy where I can help people come to that root cause analysis quick enough without losing my depth, right? Now, a hint here is root cause analysis is essentially about discovering causality. It's about finding relationships. Now, I put an example here on the right-hand side. It's an example. It's not the generic case, but I want you to think about it, right? So these packets that we capture are powerful for all the four use case silos I gave, right? Performance, usage, cost, and security. The packets stay in the sense, but I've got derived metrics from that. I've got time series. I've got things like, packet drop counts. I've got retrans counts. I've got response time counts based on what application is used. I can do things on those time series. I can baseline, I can do change detection, drop detection, spike detection, what have you. As I bring those up closer to, say, where Portal now lives, I can start doing correlations and I can start doing even predictions, right? If this trend keeps going, we're going to run out of bandwidth. When the packet drops keep heading in this direction, you're going to hit that magic 2% point where basically no application can connect anymore. You need to act in the next 20 minutes, right? In fact, the last time this happened, we also noticed that this router wasn't doing well. That link was saturated, whatever. The open-ended problem presents itself, right? So the idea here is that in order for Riverbed to do good in the future, we need to allow this depth of analysis while bringing this knowledge, this causality to the operator. And so I call it peeling the onion, because I want that operator to be able to get back to those petabytes of packets that live deep and down. Now, I've got a PhD in machine learning, so I want to do a little bit of dispelling, right? We've got this AI ML craze going on, and you know, as we're building this pyramid of analysis that leaves the raw data deeper down, you know, we tend to resort to, geez, what kind of algorithms can we use? And this is where I'm going to tell you about this open-ended problem space again. So right, I can. So the day I stopped playing chess, right? It's an interesting story. The day I stopped playing chess is when I realized in college that I could write a computer program in less than a day that would beat me at chess, right? Like I did it, and it's like, okay, now chess is no longer interesting because I can write a computer program to do it better than me. Except that, you know, take a look at the self-driving cars. They were supposed to be here 10 years ago, millions of miles in a simulator, and the moment it snows outside, the thing shuts down. So we're not there yet. Why is this? Why can't we get good at this, right? Why is it that we have created these neural networks, which are modeled after the most powerful inference machine in the entire universe, known universe, I should say. Yet what we're doing with it is we're helping us correct text message mistakes, right? Like it's sort of, you know, why aren't we seeing more coming out of this, right? So I've done a little example on the right-hand side. You can Google yourself a million of these examples. 17-layer neural network doing on-par image classification. Image classification means you look at the picture, you say what the thing is in the picture. On-par means as good as or better than a human can do it. So take a look at the first one there. You know, it thinks it's a mammal, 92%. Well, you know what? I think I agree. It's a gazelle, a vertebrate, you know, might be a springbok. You know, I'm actually already lost. I have no idea what these animals on this. Yeah, that's right, Stephen. It's got pokey things on the head. It could be a deer, right? You know, so hey, it did really good. Okay, so now on the right-hand side image there, we've introduced a 10% random noise. 10% random noise. And the algorithm thinks it might be a tree, an ecosystem, or a leaf. And it's like it completely degraded. And I mean, I'm going to have to climb into my computer screen to see the difference here. Now, what has happened, right? This is the destructive degradation we see because it's an open-ended problem. Because now you can say, okay, Vincent, train the neural network on image with noise in it. Yeah, that's fine. But then I take the picture day and night. Then I take the picture with two of these springboks standing next to each other, and then it will fail, right? So this is a very common problem. It's the open-ended problem, right? And this is exactly where neural networks and AI struggle. And that is exactly where Riverbed has always had its highest value to people, right? So to operators. So that is the problem to solve. So very careful usage of understanding which problems these methods do well at, right? Making the computer do what the computer is good at, allows me to leave open the space for the operator to do what they're really, really good at, which is inference about open-ended problems, right? So this is something to be used very sparingly. So what do I mean? I just put this up as yet another example, right? I want you to get sort of that gut feel on how am I going to approach that. You know, there are things that can be done closer to the data, right? Like baseline creation, standardization of this data, what have you, sensor drop detection, anomaly voting, etc. You know, I can let the sensor do that. I can let an AppResponse or a profiler do that, keep my depth in the data there. As I'm starting to move closer to the portal end of the spectrum, I can start doing the threat analysis, the correlation, right? What is in my policies? You know, how do I want the user to interact? I can data mine, I can find those root causes, right? The key to Riverbed's future is the knowledge bubbles up while we keep our depth available to the operator. All right, so here's the same picture, and I'm gonna come to a conclusion here. Here's the same picture that you've already seen from Phil, because I want to put that back together for you. This is essentially the same pyramid I was showing to you earlier. As we move into a world where the complexities grow because they're no longer as one beautiful single point, right? And this is to what Enrico was saying earlier, one single point where I can capture this data. I'm going to have to create a patchwork. And when I create a patchwork, it is about normalization. It's about overlapping angles, which is what we showed earlier and talked earlier about how powerful that is. And it's about incomplete data and doing inference in incomplete data. Those three things together scream open-ended problem to me, which is exactly where we need to be, right? It's exactly where we can provide help because that problem doesn't go and solve itself. So what does that mean, right? That means we'll be pushed more to the endpoints. We are going to, in addition to what we're already really good at on the network, we're going to be looking at infrastructure as a service telemetry. We're looking at container orchestration and container monitoring infrastructure. We're looking at what is an endpoint, how does the endpoint connect? We're looking at how does the SaaS application perform? And by bringing all those pieces of telemetry together in a logical way with our flows or packets or synthetic test data, we're starting to create a patchwork that necessarily is going to have holes, but by bringing it together in a central place like Portal and doing this inference, we can start to show patterns that can help that operator come to that root cause analysis.
Sorry, don't you think that that's a almost unconscionable deluge of data, right? Coming into the portal. I mean,
yeah, and I think that's the point I was trying to make. For us, what is really important is raw data, full fidelity raw data stays behind in the sensor, while the knowledge we discover is brought to Portal. That's the only way to keep this manageable. Right? This is why I tried to show the pyramid in two different contexts. It's a hard concept to sort of grasp with, but imagine you're collecting raw packets, and out of that I get 150 different time series, and each of these time series are minute by minute. These time series that can do anomaly detection on. Well, I don't really have to actually bring every single time series back to Portal. I mean, I might, but I might do it on a 5 minute by 5 minute basis, whatever the granularity is that the operator needs at that time. Now, what I will bring is there's a bimodality in the link status here, meaning the link is either 10% full or 90% full. And every time it goes from 10 to 90 and back down to 10, that's information, right? That's data mined surfaced information. That needs to go to Portal because that might correlate very strongly with poor application performance that we're learning from a synthetic test. And that in itself is a change detection or anomaly detection algorithm. It says performance is normally just fine, but now it's different. And now I've got only two pieces of data that I can temporally put together for the operator. So I think what you're getting at is like, it's an impossible volume of data. And I think that you're catching on exactly to the story I'm trying to tell. The key to our future success and strategy is in managing that data volume and discovering information, knowledge, as opposed to raw data, so that only the stuff that matters to the operator makes it all the way to the top. So it's a bit of a story. It's a story of a future. It's a story of bringing breadth while maintaining depth. It's a story of we are evolving with our users to the places where our users are going, right? Which is, all the technologies that you have pointed out, right? We have to prevent us from going blind. It's also a story of how our existing assets in packets, flows, synthetic tests, NetIM, what have you, they remain powerful assets. They have value in the cloud, but we're augmenting that with more modern or more, with where the customer is shifting to, right? So, so that's sort of the story of where Riverbed's going into the future. We want to deliver that root cause analysis, that insight without loss of depth. And that's the strategy we have for it. So that's what I have to share with you today.
So Vince, I have a question about that data volume. You're noting that that's a challenge, but that's something that you're doing deliberately, is trying to capture all of it. If we're after insight, is there a way that we can do that by capturing less data and only capturing the stuff that we actually need, rather than let's just collect all of it and then throw it at some fancy machines and they'll do machine learning on it and then figure it out for us because it's too hard?
Well, Justin, I'm glad you recognize that our machines are fancy, but the point there is that I think that one thing that we have overwhelmingly found, because I am exactly with you on this. It's like, It's going to get some derived metrics. We're going to boil those things down. We'll find the correlations. We're done here. And pitching that story, the customer has always told me, yeah, but then what if, right? And then usually some crazy scenario came out like, well, you know, that's great because we already got a tool that does that. I'm like, oh, I don't want to build another tool that already does it. Well, what do you do? Okay, so here's a user. The user is in Paris. Okay, user is using Caspi, and they're trying to go to the Google Suite. I don't know, right? Users reporting really poor performance. Okay, what do you do? Okay, well, we looked at it, and Google Suite says it's all green. The Caspi says we're all connecting fine. The system is not overloaded. Okay, what do you do next? Well, we captured packets. Really? Well, what did you do with those packets? So we took a look. We noticed the Caspi was onboarding through Singapore as opposed to going straight to Sunnyvale. Well, that's interesting. What'd that do? Well, that cost these packet drops, those delay, what have you. And so the thing is that the story I get is that the operator wants the option of returning to that depth. And we're kind of in a luxury position there, Justin, because Riverbed's got an enormous fleet of this hardware out there that is capturing this data already. We don't have to go build that. My problem is not building this massive data capture machine because that's what we already have out there. My problem is I need to get people to draw conclusions from that faster than they're doing today. Does that make sense?
Kind of, I guess. It sounds like we're our own, like there's all this data, but we don't know what any of it means. So why are we collecting it?
So that's the open-ended problem story, right? So one thing that we know, so I have a cybersecurity background. I always used to say, I capture everything because I don't know today what I need to be looking at tomorrow, right? This was so true in the Sunburst SolarWinds scenario, right? Like 8 months and nobody had noticed. Okay, how do you find out? Oh, we go back to packets, we go back to flows, we go look at what's on the endpoints, we go try to figure out anybody talk to that IP address, right? And when I look at our most skilled operators, that's precisely what they do. They don't know exactly what they're looking for when they're doing root cause analysis. They just know that they want to know everything that's odd. And because the problem's so open-ended, how are they going to need to slice and dice the data? That this is not a simple AI classification problem. It's not like I can take 100 things that can go wrong in the network and train a classifier on it. It would badly fail the moment I deploy it with a customer because all networks are different. And the usage of the network is different, and the traffic distribution, et cetera, which means classifiers cannot be trained on an open-ended problem. So far, the only technology I've ever seen solve open-ended problems well is the human mind. And so what my job is not to solve the problem by data analysis, but to do all the work I can in the computer so that the human can do that final solving of the problem with the knowledge and the background and the context that they have.